Okay, so we proved Hanban Theorem in the last class. So we will continue to discuss dual spaces in this talk. Okay, so let X be a Banach space. It need not be a Banach space, just a normed linear space. X be a normed linear space. Then X star is all those phi from X to, let's assume C. I mean, whenever it's a real line, I will tell you. Usually we'll work with complex plane. Okay, so such that phi is bounded. All bounded linear functional. B is bounded linear. Then X star is a Banach space. I hope you know this. You have proved it, but the proof is not. I mean, this follows from a more general result. If XY normed linear space, if we have XY normed linear space, and if we have suppose BXY equal to all T from X to Y bounded linear map, T bounded linear, then BXY is a Banach space. If Y is complete, if Y is a Banach space, okay. I mean, its non-linear space is clear. You have to only check it's complete. So to check it's complete, if you assume that Tn converges to, it's not Tn converges to T, Tn is Cauchy. You take some sequence contained in B of XY. If Y is, I mean, it need not be the case that X is complete. If Y is complete, then all bounded linear operators from X to Y, that collection forms a complete non-linear space with respect to the operator now. Okay, is Cauchy in operator norm. Okay, in operator norm. Okay, let me just write it. Is Cauchy, that is norm of Tn minus Tm goes to 0 as Nm goes to 0, as Nm goes to infinity. Then this implies Tnx minus Tmx will go to 0. Okay, as since Y is complete, there exists Tx such that Tnx converges to Tx. You call that limit as Tx because Y is complete, there exists limit, and call that as Tx. Then you can use this Tnx minus Tx is less than or equal to limit. I mean, you have the limit in n, you can have the limit in m and n here. Tnx, but let me just write it like this: Tnx minus Tmx. Okay. So now first you can prove that T is bounded because norm Tx is less than or equal to mod Tn minus T minus Tn. Yeah. I mean, you can choose some Tn. Okay. I mean, you can choose some Tn minus T and Tn minus Tx. And then you can, I mean, let me just, I mean, you must have seen this. Okay, you can choose some n, which is very big, and then I mean, you will only add an epsilon to that. Because this x can be chosen and assume norm, I mean, if you choose norm x is less than or equal to 1, then you will only be adding an epsilon to that. Okay, so because of that, norm t will be bounded. And from this, you can actually show that norm t is bounded and then Tn converges to T. Okay, so from this inequality, it will follow. You must have seen this, so let me not go into too many details. The point is, if X is a normed linear space, then XR is the Banach space. Okay, so if X is NLS, normed linear space, then X star, which is not trivial, is a Banach space. It's a proper Banach space with respect to operator norm. Okay. Okay, so this is not equal to 0 due to Hanban theorem. This is thanks to Hanban theorem. Now we want to see some consequences of Hanban theorem. The first one is the corollary, following corollary. X is a non-linear space, and X is in X. Then there exists a non-linear function of phi in X star such that norm phi equals 1 and mod of phi, no, mod is not needed. Phi x equal to norm x. Okay. So if you have any element and you can find a phi, you can find a linear functional which evaluates the norm at that point x, and then it's a bounded linear functional which norm phi equals 1. So it's a very useful. They usually, I will call this as Hanban theorem, and this will be very useful because we invoke it many times. So this corollary is very important. We may call this is a consequence. We may call this as Hanban theorem and use it. I mean, when I say Hanban implies this, then I'm referring to this. Okay, or the other corollary which follows this. So this is just easy. So you define phi naught from, you take x, so you take cx, which is equal to just lambda x. Okay, this is equal to lambda x plus lambda in C. Okay, this is just a one-dimensional subspace. To C, by you just define any phi naught of tx equal to t times norm x. That's all. Okay, clearly it's linear because you are just evaluating. I mean, you are just multiplying by norm x. So clearly it's linear. Now extend Hanban. There exists extension phi from, and you can see that it norm is, I mean, phi naught of norm x is x, and then I mean you can see that it preserves the norm. Okay, so it's norm of phi naught equal to 1. Okay, norm phi from x to c such that norm phi equals 1, and it extends this. So norm phi of x equal to norm x. Okay, so this just immediately it follows from Hanban theorem. What follows is something more, and I mean the corollary implies the following. The corollary to this corollary 2. So the unit ball of x star, not even unit ball, I mean the unit norm x equal to 1. The unit ball of x star separates points of x. That is, if xy, if you have xy is in x and x not equal to y, okay, then there exists a phi in x star with norm phi equals 1 and phi of x is not equal to phi of y. Okay, it's just clear proof. Take x not equal to x minus y and use the previous corollary. There exists a phi such that phi of x not equal to norm x naught, which is equal to norm x minus y, which is not equal to 0. So phi is not equal to 0. And phi of x, phi of x is not equal to phi of y. So norm of phi equals 1 and phi of x is not equal to phi of y. So it's clear. So it's clear.
You've written that
Say it again.
You've written that they're equal. You've written that they're equal in the statement.
I have written what? The equivalent statement.
You have written that phi x is equal to phi y in the statement.
Phi x equal to norm x naught, which is equal to norm xy. Phi x, not
before the proof.
Sorry. Yeah. Not equal to. Separates points mean they are not equal. Correct. Yeah. So yeah, they are not equal. So the point is, this says that the unit ball of x star, the dual space itself, is bigger than the, as a topological space. As I said, you say that there are many functions in some collection if they separate the points, which I mean, if they can given 2 points, you can find a function which differs on those 2 points. So this says that the unit ball itself is quite big for a dual space. Okay. So the next corollary to Hanban theorem, it not only is just separate 2 points, it separates a closed subspace and a point which is not in the subspace. So if X is a non-linear space and X naught contained in X is closed and X naught is in X minus X naught, okay, then there exists a phi in X star with, of course, norm phi equals 1 and what? And phi restricted to X naught is 0 and phi of X naught equal to norm X naught. It's not norm X naught. It will be the distance between them, okay, equal to the norm. It is equal to, you know, the distance in a metric space. You can define a distance from between a point and a closed set. Okay, it is that distance. D of X naught, which is equal to infimum of Y, maybe X is another. X is an X naught, D of X naught X, which is equal to, of course, infimum of X and X naught, norm of X minus X naught. This is what I mean. I think you haven't talked about quotient spaces. The whatever we approved the earlier one, it is just the Hanban theorem for the quotient space. That's all. Okay. I mean this corollary which we approved, the corollary 1, just applied to quotient space. When you have a closed subspace, then you can quotient it. I don't want to talk about those things. If you haven't, I mean, if you already know it, then it is basically that. Otherwise, I will directly give the definition. Proof, you define. You can take this subspace Y naught equal to X naught direct sum C X naught. Okay, and you'll define phi naught from Y naught C by phi naught of X plus lambda X naught equal to just take the lambda times I use the distance D of X naught. Okay, it's clear. I mean, then it will follow. This has all the properties. Okay, this has all the required properties. The proof is same as earlier. Okay, so as a corollary to Hanban theorem, we get that if you have a closed subspace and a point, then that can be separated by a linear function. Linear functional of norm 1. Okay. So there is furthermore consequence of, I mean, there are too many consequences of Hanban theorem. The other one is, let me make a definition. If you have X is a non-linear space, X star dual space, this is called dual space. I don't know whether I said it. So all bounded linear functional. Then you can embed this X into X double star, the dual of X star, by the following prescription. Then define for X in X, you define phi X. Maybe I use this. In X star star, which is X star star, which I call it as X star star, by phi X acting on any phi equal to phi of X. Okay. So this is just the evaluation functional. You can define a linear functional on X star. So I mean, I have to show that it actually belongs to X double star. Then what I mean, which is trivial. So then phi X mod of phi X phi equal to mod of phi X is less than or equal to mod phi times norm phi times norm X. So this implies phi X, norm of phi X as a linear functional is less than norm phi. As a linear functional, its norm is less than norm phi. And further, Hanban, we have Hanban implies there exists a phi such that with phi of x equal to norm x. Okay, this implies phi x of that phi is norm x, okay, and norm phi equals 1. So this implies norm of phi x, I mean, which is just the supremum over all norm phi. So this is equal. Let me write it once. This is just norm phi less than or equal to 1 mod of phi x of. Okay. So we have shown that this is less than or equal to norm phi. Okay. Sorry, this is less than or equal to. You should tell me when I make mistake. This is less than or equal to norm x. Okay, that's what it means. I mean, phi x is a linear functional on x star. Phi is the small phi is varying. The script phi is the one which is the linear functional defined on x star. Then script phi x acting on small phi, which is the linear functional in x star, is equal to phi of x. And this inequality shows that norm of script phi x is less than or equal to norm x. Okay. And Hanban theorem ensures that there exists a linear functional which norm phi equals 1 and which evaluates this norm at x. Okay. So because of that, norm phi x is less, I mean, norm phi x, the supremum, whatever the supremum is exactly equal to norm x. Right? We know that all these terms are less than norm x, and here it says this is equal to norm x because it attains its supremum there. Okay. Is okay. So this implies this whole thing, whatever we have done, these things implies this phi, which is a map from x into x double star, which is the dual of the dual, where x going to this phi x is isometric. I hope you know what is isometric. Isometric means it preserves the norm. Okay, that is normal. Sorry, what is it? Normal. Sure. This is equal to norm x. Okay. Isometry means it preserves the norm. Okay. So any isometry, I mean, these things are clear because I am making a mistake and you are not pointing it out. So I'm not sure whether you follow it. I hope you are. I mean, these are all very easy things. If you have seen it or if you are familiar with the Banach space language, which you are introduced in the last semester. Okay. So I'm going a bit fast. If you have any doubt or anything, or if I'm making a mistake, please tell me. Okay. So this implies that, so this is an isometry, and an isometry, the range of isometry is always closed. Okay. Since range of isometry, which I will verify here, the range of isometry is closed, this phi of x, this is contained in x double star, is a closed subspace. I mean, with respect to the closed subspace, with respect to the operator norm on x double star. X double star is a dual space. It's a dual space of the dual space of x. Okay, so it has an operator norm. With respect, that operator norm coincides with the operator norm of x on this phi of x, this range of phi. Okay, and this phi of x is closed, and range of isometry is closed because of the following. If some phi of xn converges to some y, okay, this implies norm phi of xn. I mean, if it is Cauchy, it's Cauchy is enough. I mean, we have to prove that it's closed. So in particular, phi of xn is Cauchy. Okay, but this implies xn is Cauchy. Okay, this is closed given that x is a Banach space. Sorry, for that x will be a Banach space. If x is Banach, otherwise this is not true, of course. I mean, this says that if x is a non-linear space Okay, I will come to that. If X is a Banach space, then phi of X is closed. Okay, Xn is Cauchy. This implies Xn converges to X in X. But then since phi is isometry, phi of Xn, I mean, I can put this phi Xn in the subscript or phi of Xn. I mean, it's both same thing. Okay, because it's isometry, this will converge. Phi of X, which is equal to Y, of course. Because phi of Xn converges to this is equal to Y. So this implies phi of X is closed. Closed if X is Banach. If X is complete. If X is just a non-linear space, this is a remark. X is just a non-linear space. Then you can embed this phi of X into X double star. Okay. And you can take the closure there. And that closure will be a completion for this. Okay? I mean, that will be precisely, that will be like the completion of this X. Okay. Then phi of X closure in X star is isomorphic to the completion. You know, the completion of any metric space is unique and up to an isomorphism, up to some map which preserves the metric. Okay, here up to, I mean, I don't think we have talked about completion of a Banach space, but the completion of a Banach space is also closed, which we up to isometry. Okay, so is isomorphic to completion of X. Okay. Any questions? So you want me to keep the iPad horizontal or vertical? Because you don't see too much when it is horizontal. This is okay?
Yeah, horizontal is better because otherwise
Better,
it's
no?
too small to.
This is better. Okay. 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 So what we have done is if we have a non-linear space X, we can embed it into X double star as an isometrical subspace. So if they are equal, then we call that as reflexive. Okay. X is said to be reflexive if, let me not, I mean, if phi of X is equal to X double star. And I will forget this phi. Okay, it is just the direct identification, it's just embedding. So I may say X equal to X star. Okay, I will say X equal to X star. X equal to X star. So this is what is called reflexive. Okay. So let us prove something about reflexivity proposition. X is reflexive is equivalent to X star is reflexive. If and only if X star is reflexive. Okay. X is reflexive means X is equal to X double star. So we have to prove that X star is also reflexive. If X star is reflexive, that means X star is equal to X triple star. Then X is equal to X double star. So suppose X equal to X double star. Okay. That means every linear functional on X star. I mean, X double star is a linear functionals on X star. So every linear functional on X double star, sorry, every linear functional X star is actually given by an element in X. Okay, that's what it means. So we have to show that to show X star equal to X triple star. Okay. Let I use this map phi for every Banach space. Okay, I mean this phi. I mean this phi is an identification from some Banach space to its double dual. X to X double star. Okay, so which I use for any Banach space. I mean, otherwise I may have to use different symbol and there may be a confusion. At least I will get confused because I'm not very comfortable with these Greek letters. Okay, so let us take some linear functional. Let us say chi in X triple star, which is equal to X double star star, of course. So let us take a linear function on x double star. We have to prove that it actually comes from x star in the following prescription. Okay, using that phi. Okay, but then x double star is all those phi x. Okay, x in x. That's what we have assumed because x equal to x double star, which we have assumed. Okay. So now define lambda. We want to show that this chi is actually given by a linear functional on x. I mean, we want to show that this is actually chi is given by some element of x star, which is a linear functional on x. So you define lambda from x to c by lambda of any x equal to the chi of phi x, right? It's well defined. Right. Now we will just evaluate. Now what do you want? Now claim is all we have to prove that this chi is given by this lambda. Okay, chi equal to phi of lambda. See, I am using this phi for a different Banach space now. I'm using the same phi where the map is from that Banach space to its double star. Okay, the same phi I'm using. The claim is chi is phi lambda. So you just evaluate phi lambda. You have to prove this. You have to prove that phi lambda coincides. Phi lambda is a linear functional on x double star. Okay. So you have to evaluate on some phi x, right? Because the x double star is, I mean, all x double star is equal to x. So everything is given by phi x. Okay. So phi lambda acting on phi x. That's what you have to see, which is same.
What is chi?
Chi. This chi.
Yes, sir.
This chi is a. I'm assuming this chi is an element. Where is it? Yeah. This chi is here. This chi is an element of x triple star.
Okay.
We are assuming that. I mean, we are assuming that x equal to x double star. We want to prove that x star is equal to x triple star. That's what we want to prove.
Yeah.
To prove that x triple star equal to x star, we know that x star is contained in x triple star. Okay, this we know.
Yes.
We want to prove that it is actually onto. So I am taking some element in x triple star and I want to show that it actually comes from x star.
Okay.
Okay. To show that I take an element in x triple star, which is actually by definition, it's a functional on x double star. But then the x double star, because we assumed x double star is equal to x star here, I mean equal to x here. Okay, it contains only elements of this form phi x. I define a lambda from x to c by this prescription. Okay, this is for all x in x. Okay, now I have to show that this chi is given by this phi lambda. Then it's done. That's what I want to show. I want to show that x triple star looks like all those phi lambda. That's what I have to show. So I'm saying that chi equal to phi lambda. So to show this, I want to show that it coincides on all elements. All elements of, I mean, this is on x double star, right? They are all there. I want to show as elements of chi and phi lambda they are equal as elements of x triple star, which are functional on x double star. So they're just same on x double star. X double star is made up of these elements, right? Phi x, x in x. Okay. We are assuming x double star equal to x. I mean, this phi is a kind of equivalence. Sometimes I'm not writing it each time. Okay. So phi lambda of phi x. So that's what we want to find. So which is same as phi x acting by definition of phi, which is same as phi x acting on lambda, right? Which is same as lambda of x. But then by definition, that is same as chi of phi x lambda, phi x. So chi lambda of phi x is same as lambda of, phi lambda of phi x. See, I'm always confused with this gate. Phi lambda of phi x is same as chi of phi x. So this implies phi lambda is equal to chi. So this is then, so we have proved that x star equal to x triple star with respect to that identification, with respect to this identification phi. Okay. Is this fine? It's just direct by definition. There is really nothing in this. You just write the definition, you just find that it is true. Is this fine?
Yes.
Okay. So if one person says okay, I will go to the next one. You can ask me later if there is any problem. Conversely, if x double star is equal to x double star, we want to prove x equal to x double star. Okay. Suppose not. So suppose not. That is, I mean, x equal to x double star means the image of phi we want. Suppose not. Let lambda. So now I want to define a linear function. Let chi be an element of x triple star. Okay. X triple star such that chi restricted to this phi of x, okay, equal to 0. Okay. See, we have proved something. We have proved a version of Hanban, a corollary of Hanban theorem here, which says that if we have a closed subspace, if we have a closed subspace and a point which is not in the subspace, then there is a linear functional which separates that point and the closed subspace. So it's as a, this corollary implies that if any linear functional, this just means that there exists a linear functional, non-zero linear functional, which vanishes on this closed subspace x naught. Suppose if any linear functional which there is no such linear functional, okay, which vanishes on this x naught, then x naught should be equal to x, right? That's what this says, right? If x naught is not equal to x as a closed subspace, then there exists linear functional which vanishes on x naught and the linear functional is not equal to 0. So suppose if we prove that there does not exist such a functional, then x naught should be equal to x. Okay, so that's what we will prove here. I want to prove that x is equal to x double star. I'll prove that there does not exist linear functional chi, it does not exist a non-zero linear functional chi which vanishes on this. So suppose there exists a linear functional, suppose not. So then we assume that there exists there is a linear functional which vanishes on that. I will prove that this is actually equal to 0. Okay, then that proves that x equal to x double star by that implication of corollary of the Hanban theorem. Okay. So why is this true? Chi restricted to phi x is 0. Okay, suppose this is 0. We have assumed that x equal to x double star. Now, what do we assume? Wait. What do we want to prove? Yeah, we have proved that, sorry, we have assumed that x star equal to x triple star. We want to prove x equal to x double star. So we take a chi in x triple star such that chi restricted to phi of x is 0. Okay. Then chi, but then this chi is in triple star, which is given by this. So since we have assumed this, x star equal to this, there exists a lambda in x star such that this chi is actually given by phi of lambda, right? Because we have assumed that x star equal to x triple star. Okay. Now phi lambda of any x, phi lambda, where lambda is in x star. Okay. Okay. Now phi lambda of any phi of x equal to chi of phi of x, which we have assumed that this is equal to 0. Okay, because we have assumed phi lambda equal to chi. So this should be equal to 0. But then this is equal to phi x of phi lambda. Sorry, x of phi lambda. Sorry, phi x of phi lambda, which is right. Phi x of lambda, sorry. Lambda. And this is equal to lambda of x. Okay. So lambda of x equal to this is equal to 0. This implies lambda of x equal to 0 for all x in x. This implies lambda equal to 0. this implies, but we have assumed that phi lambda equal to chi. So chi equal to phi lambda equal to 0. This chi equal to 0. Okay. So there does not exist a linear functional on this range of phi of x, which is 0. That means x should be equal to, this implies x equal to x double star. Is it okay? Shall I show you the proof again? Suppose if this exists, we assume that x star equal to x triple star. Then we want to prove that x equal to x double star. Suppose if that is not the case, then we take a chi which vanishes on this closed subspace. This subspace is closed. Then we show that cannot be anything else other than 0. So which will imply x equal to x double star. Okay, it's just a matter of writing it. That's all. Fine. Okay. So this shows that if x is reflexive, then x star is reflexive. So as a corollary to this, we will see that if x is not reflexive, or if x naught is not, one of them is not reflexive, then this x contained in x star is not equal to, that's what it means. This is contained in x4 star, not equal to this. It will go on like this. It will just go on like this. This tower will never end. Suppose if it ends somewhere, then the pre-dual of that will be, suppose if something is reflexive, something in this tower is reflexive, then the one before that will be reflexive. Because of that, everything will be reflexive, right? Because of that, it will not happen. If it is not reflexive, then it will go on like this. Yeah. Any question? Okay. Next on dual spaces, I want to do this Lplq theory. So actually, my intention was to prove LQ, the LP star. I hope you have seen LP spaces in the last semester. I know that it is proven that they form a Banach space and some inequalities, basic inequalities were proved. So, but this is not proved. The duality theory is not proved. So if for P less than infinity, greater than or equal to 1, this LP star is equal to LQ, where 1 by P plus 1 by Q equals 1. It is not proved. This is not proved, but I want to prove it. I don't see if I have to prove it for measure theory, general measure theory alpha, then I need Radon-Nikodym theorem, complex measure. I have to invoke all those things, but those things are not done for you. So I don't know whether, if I have time, I will do it later. Now I will do it for just for small LP and small LQ. Okay. I'm told that Radon-Nikodym theorem was not proved in the last semester, and then this even complex measures were also not done. So we will not do this. This will take a lot of time. So if we have time, we will do it later. Okay. So maybe later. So now I will prove only this small LP theory. Okay. So define LP equal to P is greater than or equal to 1, less than infinity. Okay. Is all those sequences xn in C and summation mod xn power P is less than infinity. Okay. So this is LP, and for L infinity is all those sequences, bounded sequences. Okay. All those bounded sequences. Then LP star is equal to LQ, where 1 by P, 1 by Q equal to 1. So if P equal to 1, Q is infinity. Okay, in that. So this we want to prove. And there is something more that you can take C0 equal to all those sequences xn, such that all those sequences xn converges to 0. Okay. And you can show that this is a Banach space. This is also a Banach space. Then C0 star equal to L1. And we want to prove that L1, L infinity star contains L1, of course, but that's not equal. So all these things we want to prove. We want to prove that LP star equal to LQ when P is greater than 1, and C0 star equal to L1, and L infinity stars contains L1, of course, which is true, of course, because L1 star is L infinity, so L1 will be contained in L infinity star by whatever we have seen, by the evaluation map. But then they are not equal. Okay, so these things we want to prove. So to prove this, you must be knowing this Holder inequality, summation mod xn yn is less than or equal to, let me call that x tilde equal to xn, a sequence, y tilde equal to sequence yn. Okay, then this is less than or equal to, take xn b. So this is in LP, this is in LQ. I hope you have seen this. Okay, this is Holder's inequality. I mean, I hope you have seen it for a general measure space. Anyway, this is not difficult to prove. You just have to use the convexity of this exponential map. And then you can prove it for some, summation, and it's very easy. It's not difficult. Okay. If you prove it for two of them, x and y, I think that is enough. Then you can prove it for this. Anyway, I don't want to go through the proof. If you haven't seen it, you tell me. I'm sure you must have seen this. Okay. So this is Holder's inequality. So which we will use here. And what else I need? I don't need anything else. So now let me state the proposition. LP star is isomorphic to LQ. Okay. Proof. So we want to define the isomorphism, and then we want to prove that, and then prove that it is an isomorphism. Okay. So for y tilde equal to yn, a sequence in LQ, define phi of y tilde from LP to C by the following prescription. By phi of y tilde acting on x tilde equal to some xn. So whenever I write y tilde or something, it's a sequence xn, x tilde means xn, okay, equal to summation x and y. That's all. So clearly phi y is linear. You can take the scalar out, you can sum and listen, so it's clear. Clearly it's linear. We have to prove that it's bounded, but then it follows from the Holder's inequality. Okay. Now summation xn yn, mod of this is less than or equal to summation mod xn yn is less than or equal to mod x tilde p mod y tilde q. Okay. So this implies phi y tilde of x tilde, which is this mod of this, is less than or equal to norm of x tilde p times mod of y tilde q. This implies the norm as a linear functional of this phi y tilde is less than or equal to norm y tilde q. Right? That's what this means. Okay. I have to prove that the norm is attained. Okay. To prove that norm is attained, I have to prove that this norm is nothing but the supremum, right? norm of Vy tilde is equal to supremum of all those x tilde in LP right, and norm of x tilde, this p is less than or equal to 1, t equal to 1, doesn't matter. Okay, this is the definition of norm as a linear function. So I have already proved that this norm is less than norm y tilde. I have to prove that this is equal. So for that, I have to only produce a norm x tilde of norm, I mean x tilde, an element x tilde, which is a sequence, of course, x tilde of x LP, whose norm is equal to 1. And it evaluates this number norm phi tilde, whatever we have, I mean this y tilde. That is, we want this to be this to evaluate that norm, right? So how do you do this? So take I want to get an xn, I want to get an element in LP such that when I apply this phi y tilde on that x tilde, I should get that number, this number, which is equal to that norm, whatever I want. So I want xn yn to, first I want to get rid of, I mean, I have yn. This yn is a complex number, which is some argument times its modulus. I want to get this mod yn. I mean, I want to get, see, this is what I want. I want an element x tilde in LP with norm of x tilde equals 1, such that phi of y tilde acting on x tilde equal to, which is equal to summation xn yn. This should be equal to norm of y tilde p, sorry, y tilde q. Incidentally, I didn't define the norm. You have to take the summation. So it's something this mod yn power q. Here I am writing whole power 1 by q.
Should it be something like, shouldn't you be taking norm of this when you apply 5y to it?
Norm of what? Norm of, right. Yeah, you have to take the norm of that, right? Correct. But then we will directly get it. That's okay. I mean, yeah, it's enough to get the norm, right?
Okay.
Correct. It's enough to get the norm. But we will directly get the number itself. Okay. So we have to get a x tilde like that. Take xn equal to. First, I want to get rid of this argument part of it. So that is the sign. You know, the sign of a number, complex number, is just that argument. Okay. Maybe I can write the argument or something. Argument of yn, which will be here. So I hit it and it will become the bar. Then I have to get this yn power q by p. If it is 0, then it's 0. Okay, I will not worry about it. Q by p times norm yn power q by p. I think this will work. So if you multiply by yn here, then you get mod yn there because you are multiplying by the argument. Then you have q by p. Let me just xn times yn equal to argument of yn. Okay. So when I multiply argument of yn with yn, I will get mod yn, right? So I will remove this. Okay. Mod yn plus yn. So here I should have mod yn power q by p by norm yn power q by p. So this is equal to mod yn power 1 plus q by p which is just q by q plus q by p, which is just q, right? Let me do this calculation just for that. So which is equal to yn plus q into 1 by p plus 1 by q, which is just q. Okay. Here norm q by p, q in by 1 by p, which is just so I will have the summation of it. This is okay. Norm yn power q by p. Now I take the sum here. So I will get norm yn power q there. Norm yn.
Denominator should be y, non-y tilde.
Say it again.
The denominator should be non-y tilde.
Y tilde, correct. Thank you. Yeah. Good. Yeah, because I am writing it. Right. So if I put the summation here, norm y tilde power q I will get, and here I have q by p. Okay. Q by p. So this is just, there is no sum here. Sorry. Norm y tilde power q into 1 minus 1 by p. 1 minus 1 by p, which is equal to 1 by q, which is just 1. Which is equal to 9. Okay, done. Very good. Y tilde p. I mean, this is norm y tilde, but it's just the pth norm, qth norm. Sorry, it's norm in LQ. Okay, so we have done. Anyway, so it's good that you are also alert, and I hope you understood. So this proves that. How much time I have? Yeah. So this proves that norm of phi y tilde, whatever we have defined, is equal to norm of y tilde. Okay. So this phi is an isometry. This map phi, whatever we define, is an isometry. We have to prove that it's onto. Okay. So suppose we want to prove that this phi, which is a map from LQ into the dual of LP, which is an onto. Okay. Maybe I'll define it like this. Define this map phi from LQ to LP star, okay, where this y tilde will go to this phi of y tilde. Okay. Now we want to prove that, to prove onto. To prove that this phi is onto, suppose we have a phi is in LP star. Then you can see that these any LP star is, I mean, these elements are here. EK is in LP, where EK of n equal to delta Kn. Okay, it's one at the n kth place and everywhere else 0. Okay, then take yk equal to phi of, this is this phi of ek. Okay, so now the claim is yk, the sequence is in LQ and phi is equal to phi of this y. Okay. So once we prove this is enough. So to prove this, what do we want to do? First, we want to prove that this is in LQ. Okay. Notice what is what? Notice phi of yk is phi of ek. So now phi acting on any xn. Okay. Where x equal to x tilde equal to xn is equal to phi of this x tilde xn can be written as summation. Xn is a number here. Okay, xn times En. This here I have written is n equal to 1 to infinity, but this convergence is in LP. Okay, in LP. See, whenever we write infinite sequence, we have to say where it is converging. So it is converging in LP. Okay, but by continuity, you can write it out, take it outside. This is just number. I mean, this is just sequence series in complex numbers. Okay, if you have n equal to this, xn also you can take times phi of en. Now this is just summation n equal to 1 to infinity xn yn. So we see that this phi takes this form. All we have to show that this yn is in L. This sequence yn is in LP, LQ. That's what we have to show. So to show that summation n equal to 1 to infinity xn yn. This is equal to phi of, we know that this is equal to phi of xn. This is less than or equal to norm phi times norm of x delta. Right. So from this, I want to conclude that yn is in LQ. I have to choose the right x. And similar to that. So what do you have to do? I have to make this term into mod yn. How will we do that? So take xn equal to you can replace xn by any xn, this is true. So replace in this inequality, replace xn by this argument or sign, we call it a use. Argument. Okay. Argument of a complex number. Argument of xn yn. And then we need a bar here, bar times right? That will imply that summation mod xn yn is less than or equal to mod phi times mod x delta. But then this supremum, see, so this is an exercise, same thing which I don't want to go through this. This exercise is this. Summation xn yn, okay, supremum over all. It's same as what we have gone through, okay? All x delta in P. In LP, okay, is equal to, you take all the y is fixed, okay, is equal to yq for any sequence. I mean, this is not just true for, if this is supremum is infinite, this is also infinite, okay. Maybe should I give it as an assignment? No, but this is same as that. No, it's okay. Let's. It's the proof is exactly same as that. You have to choose something and it will work. Okay. If you don't get it, you ask me. Okay. So because of that, this will imply that now y is in y delta is in LQ. Okay. Because of this. Is this okay? If you have a problem, you tell me. I'm just saying this exercise will imply that y delta is in LQ. I mean, this is true for even if it is y delta is not in LQ, this is true. This both sides will become infinity. Okay. Certainly, this side is less than x. Sorry, this is 1 second. Start, this is, and then norm x delta should be equal to 1. Or you have, or you can write it like this. This supremum is, I want to write. This is equal to P. Yeah. This is true. Is it fine? Anyway, think over it. It will be clear. Okay.
The way it's written, it doesn't make sense, right? Because on the left, x tilde is like x tilde is a bound variable. Like
x tilde is x tilde.
like this
Sorry, x
equality.
tilde is also fixed. Sorry, x tilde is also fixed. Then it doesn't make sense. No? Yeah. So what is the? So x tilde should be. Yeah. Sorry. What I have written is wrong. So what do you have to write? There is no superior. So this should be equal to less than. Sorry. This should be the case. Yeah. See, the point is this side, whatever without the supremum is less than norm of x tilde times norm of y tilde, which shows that the supremum is less than that because we have assumed norm x tilde is equal to 1. On the other hand, you have to show that the supremum is attained. For that, it's exactly what we have done earlier. That's what I mean. It's precisely the same thing. Okay, that's what I'm saying. Because I don't want to go through the whole thing again, which I should have written this as a lemma. Then I should have gone through this. But instead, I have used, so that's why I'm giving it an exercise. It's the same thing. Okay. See, that's what we have done here. So it's the same thing. If you use it, you will get it. Possibly replacing the y by, there we have used a y. Did we choose x here? We chose x here. Yeah. So it's okay. Corresponding to y, you choose a x and it will work. Okay. Now it's okay. I'm saying the same, whatever the computation we went through, if you use that computation, you will get it. Okay. It's the same computation. The supremum of this is equal to this. So that which clearly proves that y tilde is in LQ. Okay. So if you don't get it, you tell me. Okay. Okay. So this proves that LP. So I didn't really. There is some. Okay. So in this, this is true for p greater than 1. When p equal to 1, you have to do something here, something else. I'm sorry. So we have to choose this. So let me just. What do you have to do when p equal to 1? When p equal to 1, you want to choose something in L infinity. So you have. Anyway, so this is the one this is done. Let me just, we want to prove, we are only worried about this. Okay, supremum, this is a lambda. Okay, I write it as a lambda. Supremum of mod x tilde equal to 1. X tilde is in LP. Okay, summation x and yn. This mod is equal to mod of y tilde q. Okay, where this is true even when p is infinity or this. Okay. So we know that this less than or equal to is clear. Okay. Only we have to prove that the supremum is attained. For that, to attain the supremum, so in the case when p is greater than 1, do as before. When p is greater than 1. When p equal to 1, so then q is infinity. So you have to prove that this y tilde is in L infinity. To prove that L infinity, you just take xn equal to delta. Xn is a sequence, so x tilde equal to take xn, you take an element xn, for p equal to 1, take xn tilde equal to is delta xn, delta n and m. And you take the xn to be the one. I mean, xk tilde, xk tilde equal to delta kn. Is n equal to 1. K is fixed here. Okay. So if you use that, then the right hand side becomes RHS becomes just mod yn, right? When you take the supremum, you will get the L infinity norm. You will show that the L infinity norm is different. Okay. I mean, supremum will not be attained, but you will get a sequence where the supremum, which will give the you will get a sequence here. See, there we took a yn, where there we took a x tilde, where the supremum is attained. For in this case, supremum will not be attained in one element. We have to take a xk tilde, and the supremum will be attained on that sequence. That is also enough. Okay. So for p equal to infinity, you just take argument. Take xn equal to. So for p equal to infinity, you have to get mod xn. That's our argument of yn. That's all. Yn bar. I mean, I've given the detail. If you have any doubt, you ask me. Otherwise, you ask me later. Okay. Anyway, I will give the rest another one as assignment. This is assignment. Assignment, prove C0 star is L1. Okay. So you have to do the same thing. I mean, the C0 star is contained in L C0 is contained in L infinity. I mean, any sequence converging to 0 is bounded, of course. So C0 is contained in L infinity. And we know that L1 star is L infinity, but L infinity star is not L1, which we will prove now. So the C0 star is L infinity. To prove that, you define in the same way, but then you want to prove the supremum is attained. For that, I have given this. I mean, you take the xn equal to argument of yn bar, that will work. Okay. So this is assignment 2. You give all the necessary argument. Okay. Any question? If you have any specific question, I will repeat. I don't want to repeat, I mean, randomly. Okay, I assume there's no question. Okay, if you have question, you ask me later. So now we want to, so I have 5 minutes. Maybe I'll take 5 more minutes and prove that L infinity. So to prove that L infinity star is not L1, I prove the following proposition. You know, separability of metric spaces. So if x star is separable, then x is separable. Okay. And corollary to this proposition, L infinity star contains L1, but is not equal to L1. Because L1 is separable, that is because you take all rational sequences, summation n equal to 1 to n, finitely many of them, Rn, En. Okay, where En is the basis element, which takes the one Rn Ek, Rk Ek. Okay. No, Rn En is fine. Sorry. Rn En, where Rn is in rational numbers. So they are dense and they are countable, of course. So this shows L1 is separable and L infinity is not separable. You know that. I mean, suppose if L infinity star equal to L1, then then L1 is separable. So L infinity has to be separable, which is not the case. Okay. So L infinity is not separable because you just take the 0, 1 sequence. Sequences 0s and 1, they are uncountably many, and there is a distance between them. take sequence with elements in 0, 1. Okay. And any two different element will have the norm between them is equal to 1. Okay. So they are uncounted. And do you know these things? The real infinity is not separable and all those things. I mean, I think these are all trivial things, and I hope you know that. Okay. So because of that, L infinity star is not equal to L. Now we prove the proposition. Okay. So we want to X star is separable, then we want to prove X is separable. Okay. So X star is separable. So let phi n contained in X star is dense. Separable means there is a countable dense subset. So phi n is dense. Okay. Then we want to produce a countable dense subset of X. Okay. So choose Xn in X such that phi n of Xn mod of this. This phi n is a bounded linear functional. Norm Xn equal to 1. Yeah, which is possible, which is greater than norm phi n minus epsilon something. Given any epsilon, norm phi n minus epsilon, you can find an Xn. Okay, so we can take it to be norm phi n. This is greater than, this is possible. So this is less than norm phi n, so you can take something phi n Xn, but this is just the definition of norm phi n. You can choose something like this. Now suppose, so now take the set S equal to summation lambda n Xn, yeah, linear combination of this. Just span, rational span of that, span of this Xn with rational coefficient. So maybe I'll just write it. Finite linear combination of lambda k xk, where lambda k is in Q and xk is as before. Okay. So this rational linear span is countable. So S is countable. So and the claim is S is dense. So claim is S is dense. So we want to prove that S closure is X. Okay. So let phi in X star be such that to prove that something is equal to whole space, we prove that we take an arbitrary linear functional and assume that that vanishes on this subspace, and we prove that is 0. There is actually 0. There is no non-zero functional which vanishes on this. Okay. So I mean, we have seen that's a corollary of the Hanban theorem. Be such that phi restricted to S closure is 0. Okay. So that is, so phi restricted to S closure is 0. Okay. Okay. Now phi is in X star. So there exists a phi n k. There exists a subsequence phi n k converges to phi. Okay, because phi n they are dense, and the correction phi n is dense in X star. So because of that, there exists a phi n k which converges to phi. So norm of phi minus phi n k, which is greater than this xn k, or we have chosen this xn xk, they are of norm 1. So norm of phi minus phi n k acting on xn k. Okay, this is by definition of the norm, because norm xn k is less than or equal to 1. Okay. Now that phi of x and k is 0, we have assumed. So this is equal to, this is just mod. Okay. Now this is equal to mod of phi and k x and k. Now we have taken this to be norm of phi and k. Okay. So but this goes to 0. because phi nk goes to phi. So this implies phi nk goes to 0. So this implies phi equal to 0. Okay, this is what we want. So if you have any linear functional which vanishes on the closed linear span of this S, then that is 0. This means S closure is equal to X itself because of the thanks to the corollary of Hanban theorem. Any doubt? Fine. If there is no doubt, I will end the session in this class. We'll meet Monday. I will send you, I mean, next class will be taken by Nirupama, I think. So I will ask her whether it is okay with her. If it is okay, we will continue. I haven't asked her. Okay, she is not here, I believe. So I will ask her. If it is all right with her, then we will continue on Monday. Okay, bye.